In this problem, we are given the following circuit diagram here. We are also given that our Vg of t is 250 cosine of 1000 times t, with the 1000 being our omega. And then we are told that the variable capacitor is adjusted until the current I of g is in phase with our sinusoidal voltage V of g. This is very important, and we're actually going to come back to that later, and it's going to be a factor that'll help solve this problem. In part A, we need to calculate the value of the capacitance and assume that our capacitor value must be greater than 50 nanofarads, and then we need to find the circuit's total impedance. So to look for C, what I'm going to do is actually have an equation for the total impedance. Because if we have this impedance, and this impedance together, we can add them to a set value. And since our current I of g is in phase with the sinusoidal voltage, we know that the equations of our imaginary part is 0. It'll make more sense when we write it out in a second, but remember we are finding the z equivalent here. And then this is going to be equal to our 5 millihenry inductor. However, we're going to convert this into the rectangular form. That way we can add it, and we're going to do the same for our capacitor. First, with our inductor, we know that the formula for this is going to be J times our omega times our L. We know our omega is this 1000 here, so we can write this as J times 5 times K. A K is a kilo, and a kilo is 1000. And that's the same thing why we have this 12.5 K. It's 12.5 times 1000. Now, for our capacitor, we are going to have Z of C, and this is equal to a negative J divided by WC. Since these impedances are in parallel, I'm going to rewrite this formula so that way we can solve it and have a little bit less work to do when we write our actual equation. That means I'm going to move the J to the bottom, and we're going to get a 1 divided by J times our omega times C. Now we can write our equation. We're going to have our J times 5 times K out front because we're just adding this in. And now we're going to have our parallel part. We're going to have 1 over our capacitor, which is this, 1 over 1 over J times our omega times C. Well, we can flip this up using just very simple math and say that we have a J times omega times C. And we know our omega is equivalent to 1000, and 1000 is equivalent to a kilo, so we're just going to replace this with a K right here. Now to this we are going to add our other impedance, which is the resistor, and we're going to have 1 divided by our resistance times K. And this is the formula for impedances or resistors in parallel, and this is all being raised to the negative first power. Now we are going to look in here and combine these values. So for this, I'm going to set this over 1. I'm going to cross multiply these, add them together, and then multiply the denominators together. However, since we have this negative 1, we have the equation inside of here being raised to the negative 1, I'm going to flip this. So what would be our denominator is now going to be our numerator. I rewrote the first part, and now we're going to solve for the parallel portion. So we can solve for the denominator first and put that on top. We're just going to have a 12.5 times K times 1. So we have this up here, and now we can add our numerators and put them in the denominator. So we can see that we have a 12.5 K times our J K of C. So that is going to be that equation, and then when we multiply our 1's together, we're just going to get a plus 1, and then this is our current equation. Now from here, I want to combine these two equations. So to do this, I'm going to multiply our J times 5 of K by this denominator here. I'm going to multiply the numerator and the denominator, which currently right now is 1, by the 12.5K denominator. And then I'm going to add them together. And after we do that, we are going to get this as our equation. Now, we need to get rid of this denominator. However, we can't just multiply it to the other side because we're going to have this z equivalent right here. So what we can do instead is multiply our denominator by our denominator. However, we're going to switch this sign and make it a negative. That way we get rid of the imaginary numbers in the denominator. And once we have that, we can just set all of our imaginary numbers equal to 0. And this is because, again, the current if it is in phase with our voltage, means that our impedances, the imaginary part of our impedances, is going to be 0. So we are going to have our Z equivalent equal to the first part, which we are not changing, and then we are multiplying it by our 1 minus the 12.5 times our J times our K squared. And the reason why I'm putting the minus in front of our larger number is just because it'll make it easier when we are simplifying this. And now we are going to factor things in. So we are going to do this for our bottom part and the top part. I did make a mistake, and when I was multiplying these in, I forgot to add a C right here. There should be a C after our K because there is one right here. So make sure you note that when we are plugging it into our new equation. After we factor everything in and multiply everything together, we are going to get this equation right here. From here, we need to make sure we have no imaginary numbers in the denominator. So to fix this, since we have a J right here, we are going to square it and then bring it out of our parentheses because of this squared right here. If we do that, we are going to get a -1 because a J times a J is a -1. And we have a negative out front here, so we basically have a negative times a -1, meaning this is going to turn into a positive and we will no longer have a J in here. Since we no longer have any imaginary numbers on the bottom, we can set our Z equivalent equal to 0. And now this is going to be equal to the entire numerator. We don't need to worry about the denominator anymore. With this being equal to 0, all we are looking for is the imaginary numbers that are J. So anything that doesn't have a J inside of it, we are going to not involve in this equation. Just like with this bottom part right here, we're not involving any of this stuff. So when we look at our new equation, we can see that we have this 12.5K, and there's no J in it, so we can cancel this out. As well with this negative 62.5, we're canceling it out with this positive 62.5. And now we are just left with the following three values. We're going to write our new equation, and we're going to start with this C squared first. And then to this, we are going to add this right here, which has our C in it. And lastly, we have this J5K we are going to add as well. So this is going to be our new equation set equal to 0. To solve for this, we are going to use the quadratic formula. We know that this first part is equal to A, we know this next part is equal to B, and this last part is equal to C. I'm also going to simplify this by getting rid of the K's. So I'm going to get rid of the K on this J5th, and then this one is just going to be K squared, and this one up here is going to be K to the 4th. From here, I'm also going to cancel out the J's, and now we can solve for this. Remember, the quadratic formula is negative b plus minus the square root of our b squared minus 4 times our a times our c, all divided by 2 times a times c. Also remember when we are plugging this in that 1k is equivalent to 10 cubed. So for the first part A, we're basically going to have 10 times 12. For the next part, we're going to have 10 times 6, and that is because our k, again, is equivalent to 10 cubed. Also accidentally wrote a c in here, which there should not be, just a 2a in the denominator for our quadratic formula. And in solving this, we are going to get two equations. We are going to get that our c is equal to 1.6 times 10 to the negative 7, and this is in farads because capacitance is measured in farads. We are also going to get that our c is equivalent to 4 times 10 to the negative 8, and this is also in farads. Now we are told that our capacitor must be greater than 50 nanofarads. So when we look at this, these are both in farads. To convert it to a nanofarad, we're going to multiply this by 1 nano over 10 to the negative 9. When we look at this first capacitor right here that we got, the first capacitor value, if we cancel out this 10 to the negative 7 and divide it by this, we're going to get 10 to the negative 2nd on the bottom. And this is basically going to be 10 squared if we flip it to the top. So if we move this over, we can see that we're going to get basically 160. And this is greater than the 50 nanofarads. If we do the same thing to the bottom, we multiply this by 1 nano over 10 to the negative 9. We are going to divide these out, and we're just going to get 10 to the negative first on the bottom. Well, if we move our decimal over here one, we're going to get a 40. And 40 is less than our 50 nanofarads, and since our capacitor value must be greater than 50, we know that the first answer right here is going to be our answer. However, we need to rewrite this because our question asks us for microfarads. So we are going to say that our C, because remember, this is the equation that we want, is equal to 1.6 times 10 to the negative 7 farads. Now to convert it to microfarads, which it wants us to, we're going to have 1 micro over 10 to the negative 6. We're going to divide both of these out, and we're just going to be left with a 10 to the negative first up top. We move the decimal place over 1, and we will get that our C is equal to 0.16, and this is going to be microfarads. So this will be the answer for our part A, 0.16. In part B, we want to find the circuit's impedance at the value of the capacitor found in part A. This is asking us for the entire impedance of our circuit diagram. And to do this, we are going to use this formula that we created in here. However, we are going to plug our C in now that we know it. We know that our capacitor is going to be a 0.16, and our microfarads is going to be 10 to the negative 6. And then to this, we are just going to add our 1, and this is all in the parenthesis here. Now in the denominator, we are going to multiply all of this together. And if we do that, we are going to get a 2. So now we can rewrite our Z equivalent. And in the denominator, we're going to have our 2j plus 1. I did not mention the j earlier, I just circled it here, but really the denominator should have a 2j right here. And this will be our new equation. We will now have to solve for it. And to solve for it, what I'm going to do is multiply our j, 5k, by 2j plus 1 over 2j plus 1. That way we can combine both of these separate parts together. And this is going to be our new equation here. Now to solve this completely, we are going to have to convert it into the polar form. And to convert these two rectangular forms into polar forms so that we may divide them, we are going to use that our Vmax is equivalent to the square root of our real number squared plus our imaginary number squared. And then we're going to get the angle, which we're not really going to use in this case, but it's equal to the tangent -1, and then in parentheses we have our imaginary number divided by our resistance. And if we do this, we are going to get this as our new formula. Remember, when we are dividing the polar forms, we are going to divide the numbers and then subtract the lower angle from our above angle. If we do this for our magnitude, we are going to get 2,500 with an angle of 0 degrees. If we convert this back to rectangular form, which we would use the number and then in parentheses the cosine of our angle plus the j times the sine of our angle, and this will just give us 2,500. So this is going to be our Z equivalence. And that is how you would go about solving this problem. Everything on the right is for part A, and then everything on the left in green mostly is for part B. If you found this material useful, consider giving it a like. If you want more network analysis problems, there's a playlist as well as notes that cover this material and will help with the entire coursework for this subject in the description below the like button.